I'm back in the lab again. The computer, someone else in the other classroom. So, yeah, sitting here, I don't know, watching a little bit of YouTube and doing some VHDL. So I thought I wanted to show you how this works. So yeah, you guys were right. It was the game of life. Do setup do that sets up the Kesta is this program called Kesta. Well, that's the same as I used at home, as I've shown in the other videos, called Model Sim. So it's just a different kind of version. And then you run DefSim for this simulator, and look what happens. So it runs. Actually, what happens is that it simulates like this, as I've shown you before. But the simulator is then picking up, like it looks at the program counter, for example, and it looks if that's correct, and then it checks that you, yeah, and also it checks the register file, and you can see it changes, and it stops when the register file is no longer a match or the program counter is wrong. So here you can see this register is different, so the program counter is the same. So you can see that the model, or my model, says 00 with an A. This one says A with a 1. And the reason is because I haven't implemented the ORI instruction yet. So that's OR immediate, and it takes some vector, which is in fact this register file, and you should OR 1 into it, so it should look like this when it's finished. So yeah, so that's what I'm doing. So yeah, I'm not going to show you everything, of course, but in this MIPS file where I add the architecture for the MIPS, so that's all the instruction decoding and stuff, I have a type, and I add types as I figure out I need more. So there's a process called pwrite, and that process basically controls the reg file. So depending on if it's a load instruction or not, it takes data from the ALU. So if you look at the diagram, you can see that we have a certain amount of multiplexers, and an if statement, it's kind of a multiplexer, you know, or a case when, for that matter. So here we pick out all the operands from the instruction, the opcode, operands, and some instructions are special, so therefore you need a funct also. This process is instruction decoding, so basically it recognizes the instruction word and then sets the type to which one it is. And also it sets some memory control and such like that. So for example, if you want to write to data, store word in memory, then you have to set 1 on the D write bus, so data write bus, and so on. So now to the ORI, let's find, I haven't added that actually, so I don't know how long this video will be. Probably I won't be able to do it while I'm talking like this, but so an ORI is, you can there's a web page, let's see, called MIPS converter. So if I look in my simulator and then I look at the ORI instruction, this is the 32-bit operand, opcode and operand. And then I go back to the converter and then just paste it in here. I think it's the same one. Convert. then you can see. Also, you can, of course, you can use the instruction manual though. So let's do that actually. But sometimes these instructions are not real instructions. I don't know really why they did that. Sometimes, for example, if you get a move instruction, it's not really move. It's add the value plus 0, which is actually a move. So anyway, here you can see. So it wants these two operands. So this is a register. It's an indirect address anyway, but it's source, target, so the target address. So if you can see down here, you see this is the register file, and this is the specific registers of those 32 registers available. So in my case, this is called rdata. You can see here you have rdata 1 and 2, which is A and B though. I don't know why they have several names in the lab and the code and what's in this figure. So what you do is that when they say RS and RT, then it's actually the address RS comes in here, here I think, and RT either here or here, and then it looks up that register file and puts those out on rdata A. So if we go down here into the ALU, then if you look what I've done earlier, for example, we need, if you're going to do some calculations, this is the ALU. We want to tell it how to calculate. So I don't think it's a good idea to do that now, because this takes time, and I'm just making a short video. Hold on, I have a pause function. Okay, we need to decode it. So here we decode it when, and then we pick out the instruction word, and then go back into the converter. Convert, or we just take this word, because I've looked it up in the manual. We are in the instruction decoder, so you can see that on the top. So when the instruction is this case, then we want to say instruction type is ORI. Also, we need to say, okay, I'm just copy pasting from further down, that the register file enable is going high because we want to write, and the reason why we say that the target is vAddr, that comes from the here. You see at the bottom, yeah, here you see vAddr. So you have to say which register is going to be written to. So now I got a bit confused actually why we have these three though. Okay. And finally, you also have to look at the program counter, which is connected directly to the instruction bus. So you have a next program counter and then a program counter. So program counter is equal to next program counter. So basically every clock cycle it updates. And normally it will just jump 4 every time from this value. And then sometimes if you're doing a branch, it will then, if it's a relative address, it will take the address plus the address given in the operand. And if it's an absolute jump, then it will not use the next PC. So, and this is mapping, so, or offset. But for Ori, we are not going to do anything in here. Ori to work, and look, it fails again on Ori. But you can notice one thing. The first time it says 1000 as the O-ring word, but now it says C, and that means the most significant bit has been set. And why doesn't that work anymore? So you see, this one is correct, but now we got lots of F's. And why is that? Well, I can show you. So yeah, so the immediate is a so-called signed, what is it called? Signed extended. So immediate, it comes from the MIPS instruction, which is 16-bit, and then usually it has the last bit is the sign. And when you put that into the 32-bit word, then you add those sign bits over here. Then you have signed extended, but this one says 0 extended to the left. So, so I needed to do that. So how did I do it? Oh, by the way, that's why you got all these F's there, because it was signed extended, but it's supposed to be zeros. So it's supposed to be A000 as the result. So let's go back to the code, and you see immediate, and I made another immediate called 0 extended, and there you can see I basically had zeros to 31 to 16 of the 32 bits. So, and the first 16 bits are iData, directly from the iData bus. So yeah, so so if I compile it, save it, and then compile it again, it should it compiles. Okay, do setup, do reload. Let's see, devsim. Look, now it worked. Now it stopped on load word. So loading I haven't figured out yet, so now I will have to work on it. So thank you very much for watching. Maybe I can show you the end result.